Hey guys, welcome back. We're continuing our states of matter. We're up to gases now. Gases are cool, by the way. I would say that they have all the beauty of solids and they have all the beauty of liquids with a couple of new effects unto themselves. Some of these effects we need to know just for safety purposes, and another one just for entertainment. Going up in a hot air balloon or whatever. So, anyways, let's start our little lecture on gases. I hope you enjoy this, and let's get going. So obviously, the gases that we're most familiar with are the gases in the atmosphere. So here's the Earth right here. This is a picture from space. This is the one of the space shuttle missions. And you can see this is the edge of the atmosphere right up here. Below this is what we all live in. Above here is everything that we can't live in. Clouds and so on and so forth. And it's actually just kind of this little thin layer on the surface of the Earth. So when we think about gases, we usually think about air. Air is in fact a mixture of different elements and compounds. If you can recall from one of our earlier lectures on the atomic nature of matter, we discussed what mixtures are. Here's another version of gas. Some people, this is actually referred to as the gates of hell. This is in southwestern Asia. I believe it's in Kazakhstan. And what this is a natural gas rupture. The natural gas is leaking out of the rock, and the Russians, who were actually exploring this area for natural gas, when they drilled the hole here, the hole collapsed, and this gas bellowed out. And so they lit the gas on fire, thinking it would burn the gas off. It's still burning. Several decades later, I believe the originally was lit on fire back in the 1970s. So here it is, it's still burning 40 years later. All of this is natural gas coming right out of the rock. And of course, not only does it occur artificially, you get these gases burning here in the earth. Sometimes you can get volcanic eruptions. This is a major volcanic eruption. You can see the gases are coming up and rising through the atmosphere, and in doing so, it actually has an effect here on the stratus, or on the stratus clouds. I believe they're stratus clouds right here, as well as some upper atmospheric effects as well. All right, so let's start talking about what the atmosphere is. We talked about how it's really a mixture of air, but it has a couple of other processes that are happening that we need to be aware of, or a couple of properties, I should say. First off, the atmosphere is an ocean of air, and this is a really good way of describing the atmosphere. As an ocean of air, it's not just oxygen, it's not just carbon dioxide, it's not just nitrogen. It's all of these things mixed together, just the same way that the ocean has dissolved salts in it. It's not just pure water. And like the ocean, if you go down to the bottom of the ocean bottom has a lot of pressure. Well, it turns out the atmosphere has pressure at the bottom of it too. Okay, so there is in fact air pressure that we need to be aware of that exists all around us. Okay, it was a cool experiment that was devised in the mid 17th century, and actually in 1654. A demonstration done with these two spheres, and these are the original spheres to demonstrate air pressure. And this was a vacuum pump, one of the first vacuum pumps ever produced. There was one slightly earlier that goes back to Italy. But anyways, this is I believe a German design that came out a little bit later, and by Otto von Guericke, I believe is how you pronounce that. And basically what they did was they took these two spheres, they stuck them together here with some type of seal, and then they created a vacuum here. So it's like two suction cups put together, but they're just steel, they're metal. And what happened is they attached teams of horses to one side and teams of horses to the other side, and then tried to pull the thing apart. And they were unable to do so. Well, of course, once you released the pump and let the air back into the spheres just fell right apart. And what he was demonstrating, what Otto von Guericke was actually demonstrating, was the atmospheric pressure, the force that the atmosphere exerts on the surface of these two spheres when there's nothing in the middle to counteract that. There's no counterforce. Right? So it's all force going in one direction. These, like I said, these are the original ones, and you can still see them in the museum. And if you ever get a chance, you should check them out. I've never seen them. I believe they're in Europe. So atmospheric pressure is basically caused by the weight of air. It varies from one locality to another. It's never the same, it turns out. You get areas of high pressure high pressure and low pressure. So this would be a different pressure zones all across the the Earth at some given time. And of course, we want to know if it's high pressure, low pressure. We can look down here. Turns out the blue areas are the lower pressure, and the hot or the red areas that look hotter are the higher areas of higher pressure. Okay, and so that's how this maps out. So this would be a high pressure zone, and these would be low pressure zones here. Measurements are used to predict weather conditions. Things tend to flow. Air tends to flow from zones of high pressure to zones of low pressure. And so you can make predictions of what's going to come with that, looking at atmospheric pressure. So let's schematically work out what it means to have pressure. We just use this word pressure, and we've used it since we were kids, but I don't know if we've ever put a formal definition to it. So let's go ahead and do that. So pressure exerted against bodies immersed in the atmosphere result from the weight of air pressing from above. So here we can imagine there's a square on a table here, and there's these cubes of air. They're basically stacked up, and they go all the way to the edge of the atmosphere, all piled up. And all that weight is suspended right here at this, say, this table surface right here. So at sea level, the amount of pressure is 101 kilopascals. And that doesn't really mean anything until you know what that means, right? So 101 kilopascals, that's the weight of air pressing down on 1 meter squared at sea level, is about 100,000 newtons. That's a lot. That's a lot of pressure. Remember, 100,000 newtons was enough to hold those two spheres together and prevent them from ripping apart when two teams of horses were trying to pull them apart. So this is a lot of pressure, a sufficient amount of force pressing down to be able to hold them together. Okay? So I like this demonstration right here. And of course, how much force is being pushed back up by the table? Well, it has to be sufficient to be able to deal with that. We call it the normal force. We've talked about that in a previous lecture as well. So pressure at the bottom of the column of air reaching to the top of the atmosphere is the same as the pressure at the bottom of a column of water 10.3 meters high. So if you take a column of water 10.3 meters high and put it next to a column of atmosphere, they would have the same pressure measurement at the bottom. All right. The highest the atmosphere can push water up into the vacuum pump is 10.3 meters. So that means just sucking the air out of the top of, say, a tube will only draw the water up 10.3 meters. You can't go any higher than that because the atmospheric pressure isn't sufficiently high to be able to raise it up. At that point, it gets into equilibrium. So mechanical pumps that don't depend on atmospheric pressure don't have the 10.3 meter limit. So here we see some children that are pumping water. The water is coming out. It's coming out at a depth probably about 20, 30 meters. It's a lot further down than what we see here as a vacuum pump. So they're not creating a vacuum here. They're actually pumping the water. The pump is actually down at the bottom of the well. It pushes the water out rather than sucks the water out. And so that's how most water pumps work. Another way that we measure pressure is to use something called a barometer. All right, so a barometer is a device to measure atmospheric pressure. This is a schematic diagram of a barometer here. We're going to go over what this is all here in a moment. It consists of a mercury tube upside down in a dish filled with mercury. So here we have a dish, and here's a tube. Imagine a test tube of some sort, and we've got it suspended into this tube. All right, and mercury, of course, is a liquid metal that is naturally occurring. It's an element on the periodic table. The height of the mercury column tells us the atmospheric pressure. And so we can go ahead and we can dump this thing up. We usually standardize it at about 760 millimeters of mercury is standard air pressure. And of course, this is a vacuum up here, right? It's only going to let it fall down so far. So the weight of the mercury this way is being counteracted by the weight of the atmosphere over here. And so we see a balance between these two. So the mercury column exerts pressure on the mercury in the dish, okay? Atmosphere exerts pressure on the mercury in the dish. That's what we see here. The two pressures must be equal, all right? This is pretty standard Newtonian physics in play. We don't really need to go into the math of it. But an average atmosphere pressure is usually at 760 millimeters of mercury. All right, so from some of the experiments, actually going back to the hemispheres that we're describing that have the vacuums in there, it was from those experiments that Boyle's law later, through some papers and through some observations, was finally worked out. And Boyle's law is the notion that pressure and volume of a gas enclosed in a space are inversely proportional. This wasn't known at the time until Boyle's law came out. Boyle's law, Boyle actually lived at about the same time as Sir Isaac Newton. There was a lot of really smart men. As a matter of fact, Boyle knew Newton personally. So these guys were all working on different parts of physics and answering different questions. So if you increase pressure, the volume will decrease by the same factor. Example, if pressure is double, volume will half. Okay, so here we see this thing is being reduced by half, and you'll notice the needle goes over and the pressure goes up, right? So pressure and volume are inversely proportional. And this is kind of a mathematical way of showing it. The product of pressure and volume of a given mass of gas will always remain the same. So here we have a large pressure, here we have a small volume, and it's the same thing as multiplying it by a small pressure and a large volume. You know, if it's 1 liter times, 3 atmospheres times 1 liter is the same thing as 1 atmosphere times 3 liters. It's going to give you the same product. All right, so those are kind of important concepts to get out of the way. Let's get into some really important things. First off, we've talked about buoyancy in water in a previous lecture. So if you haven't seen that, you need to go back and watch that lecture on liquids, where we talk about buoyancy in liquids. It's the same principle, it's Archimedes' principle, and it applies to air as well as liquids. So basically the principle, this is just a quick review. Again, if you haven't seen it, you need to go back and see it and review that, where we talk about it in detail. But states that an object surrounded by air is buoyed by a force equal to the weight of the air displaced. Okay? And then the rules, which are the same as that for objects floating in water, is when the weight of air displaced by an object is greater than the weight of the object, it rises. When the weight of air displaced by an object equals the weight of the object, it hovers in air. It basically floats. And when the weight of air displaced by an object is less than the weight of the object, it is not supported by air, it falls. And so, of course, here in the background, in case you haven't noticed, this is a hot air balloon, or at least a side view of a hot air balloon rising up into the air. And there's lots of really great images online that demonstrate buoyancy in air using hot air balloons. All right, with that said, we can now move straight on to Bernoulli's principle. So Bernoulli's principle was discovered by a guy named Daniel Bernoulli, 15th century Swiss scientist. And it states that when the speed of a fluid increases, internal pressure in the fluid decreases, and vice versa. So it's a relationship between velocity and pressure. And it applies to smooth, steady flow, and this is called laminar flow. So this is in contrast with something called turbulent flow. We're going to describe what turbulent flow is here in a minute. And usually to demonstrate laminar flow through a system, we use something called streamlines. And these are thin lines representing fluid motion, so imagine these things. These lines right here are the streamlines. Closer together, flow speed is greater and pressure within the fluid is less. So even though, the lines are closer, there's an increase in velocity, but there's a decrease in pressure that occurs right here. So this is actually under greater pressure. And this is under greater pressure, but this is under less. So wider flow speed is less and pressure within the fluid is greater. Okay? There's some really cool effects that come from Bernoulli's principle. And we're going to describe some of them, and one of them can save your life. There was a famous case where a poor girl was killed in a terrible train accident. We're going to describe what happened to her shortly, just not too long ago. And if she had understood Bernoulli's principle, she'd probably still be alive today. Not to make light of her situation, but we can all learn from some of these things, because these situations where we could get into trouble with Bernoulli's principle happen around us all the time, and I guess we don't always take them seriously. So here we see laminar flow, smooth, steady flow of a constant density fluid. So here we see laminar flow. These flow lines or streamlines are coming straight across. So the atoms that are here will be over here. But in turbulent flow, this starts to kick in once the flow rate gets a little high. And what will happen is this will start to flow over here, and it'll create little eddies. And it'll actually slow down even though the rate or the mass of water that's moving through here is greater. And so this becomes a chaotic flow system. And it's really not the way that you want to do things. So here we see this is an airplane wing, and we see gases flowing past it. You notice that it's laminar flow underneath and it's laminar flow above, but look what's going on right behind the wing. A big eddy of You guessed it, turbulent flow. What do you think the pressure is like under a turbulent flow system? Now think about that a little bit as we go forward. All right, so applications of Bernoulli's principle. So blow on top of a paper and the paper rises. Reason? Because the pressure of the moving air is less than the atmospheric pressure beneath it. Okay. Convertible car roof puffs upwards as air moves over its top surface. If you've ever been in a convertible, you'll realize that when you're going down the highway, for whatever reason, it turns out it's Bernoulli's principle, the surface of this, usually of the tarp, or the tarp-like cover on the convertible, starts to puff out. It doesn't push in like you would expect, and that's because of Bernoulli's principle. Pressure of air moving on the top surface is less than the atmospheric pressure inside the car, so it puffs out. So wind blowing across a peaked roof, saying of a house, can lift the roof off the house. So the reason is pressure is induced as wind gains speed as it flows over the roof. The greater pressure inside the house lifts the roof up, Bernoulli's principle. So you can, where I'm recording this right now is in Waimea, Hawaii, and we get the tropical storms all the time. As a matter of fact, as I'm recording this, there's a tropical storm about to approach the island now. Anyways, this wind will come across, and we need to be aware of the fact that when a hurricane was to strike a property, the most susceptible part of the house to fall over is the roof. The roof is the part most likely to actually rip off, and it's because the internal pressure of the air or of the house is working against the overall dynamic. It's actually trying to push the roof right off. This is not necessarily a good thing to have to deal with, but it's Bernoulli's principle. It's something we have to live with. It's physics. Okay, and then of course a perfume atomizer. These are these little ball things that are used to basically spray out perfume. And the way that these work is, air rushes across the open end of the tube when you squeeze the bulb, that bulb, reducing pressure in the tube. Atmospheric pressure on the liquid below pushes it up into the tube, and that's pushing it up then atomizes it on out, and you can spray it, on your neck or wherever it is that you're going to apply perfume. All right, so I was going to talk to you about that tragedy. I'm going to go ahead and bring it up. This occurred in 2013. The first time I was teaching this class. As a matter of fact, this event occurred right when we were teaching on this unit. Anyways, so Bernoulli's principle had this tragic ending that trucks passing closely on a highway are drawn to each other. And trains do this also. She was actually, in fact, hit by a train. Knowing this can save your life. So if you're walking on the side of a road, you need to be aware of the fact that a big truck going past you is actually going to have this effect of drawing you in towards it. The reason is air pressure between the trucks is less, or trains, is less than the pressure on the outer sides pushing inwards. So what is the effect? It's going to draw you in. Anything that's physical is going to cause, the air is going to actually be drawn in towards the train, and as a consequence, it's going to pull things in. It's going to give you a sensation of being sucked in, but you're actually being pushed in by the wind that is moving towards the train. And this poor girl here was a poor victim of this. She was near a train. She kind of jumped off the track and dropped her cell phone. And in the effort of trying to go back and get her cell phone, she got too close to the train sucked her in, and she was unfortunately killed. And this is some images from that event. This is the train, and this is the girl with her mom. So anyways, the reason why I bring this up is in a lot of states, including Hawaii, where this is being recorded on the Big Island, a lot of people walk on these very narrow highways, and large trucks travel on these roads, and people are in very close proximity. If you see a large vehicle, a train, a truck, in some cases even a speedboat, a fast-moving ship, get out of the way of this thing. Give it a wide berth, because it's going to actually draw you towards it. Whether you're fishing or you're walking, you need to be aware of Bernoulli's principle. Naval ships have a problem with this all the time. Risk of passing ships colliding sideways. The reason water pressure between the ships is less than the pressure on the outer sides pushing inwards. This is the same principle. It's just now encased in water. In the Navy, one of the big problems they have is fueling ships will go parallel with the warship that they want to fuel. And because they're doing it, the Bernoulli principle kicks in, and the ships start to drift towards one another. And so the captains of both vessels need to be aware of the effect and be able to steer the ships and counteract that effect as they're going forward. It does not mean that tragedies have not happened. There have been numerous naval tragedies that have been attributed to Bernoulli's principle, and an expert needs to be at the wheel when these things happen. So there's a series of experiments I want to go ahead and show you here on YouTube at this web address, and you can go ahead and pause the video and write it down if you have an interest, but we're going to go ahead and watch it here in this video, and I think they're worth checking out. They really demonstrate the point. So yeah, that set of experiments kind of demonstrates all the different processes that we've been describing in terms of where the pressure is going to be as a consequence of velocity. So you now know Bernoulli's principle. Be safe when you're walking out on those roads. You can see he was blowing that air right between two cans, two aluminum cans, and they were drawn right to one another. Okay, so that's not something that a lot of people would predict. You would think that the rushing air going past that situation would blow the cans out of the way. It's just not the way that physics works. So Bernoulli was a smart person to be able to figure this out, and unfortunately, a lot of people have yet to learn this and to learn how to be safer as a consequence of it. This is incidentally also one of the reasons why you put dividers in the middle of highways, because as two cars pass each other, the divider, in theory, will separate the air to keep the two cars from kind of pulling in towards one another. So there's that aspect as well. All right, so we've talked about the Bernoulli principle. It turns out there's a fourth state of matter, and it's easiest to talk about it when we're talking about gases. And basically, plasma is an electrified state of mass, right? It's neither physical, or I shouldn't say physical. It's neither solid, it's not really a liquid, and it's not really a true gas either. It doesn't have the properties of all of these things. It has a whole different set of properties associated with them. So what is it? First off, a plasma, let's go ahead and give that definition here, is an electrified gas. It's kind of the best way you can think of it. The atoms make it up are ionized, and they're stripped of one or more electrons with a corresponding number of free electrons. In other words, moving through the plasma are free electrons that balance out the missing electrons that are on the ions. So overall, it has a net neutral charge. It's not a charged material, but the individual atoms within it might be. This is abnormal from everything else we've described, and that's the reason why it has very different characteristics. Where do we see plasma? Well, hopefully you recognize this. This is a really important feature in our solar system. This is our sun. Okay, there's a solar flare coming out, and all over the surface of this, especially stuff radiating out, but even everything within the sun itself is actually, in fact, a plasma. This is another plasma. This is created in a laboratory. This is a Tesla coil that's back here, and they produced a plasma that they've gotten a really nice image of, and it's emitting a purple light. I think that's one of the coolest pictures I've ever seen. Another place where nature makes plasma is the interaction of some of the stuff that is emitted from the sun, the solar radiation, basically interacts with our magnetic field in the Earth. And we get something called the aurora borealis and the aurora australis, which is the southern lights, the northern and southern lights. And these are glowing plasmas in the upper atmosphere. And this is a really great picture, one of the best pictures I've ever seen of the aurora borealis. This is in the northern hemisphere. And the range of colors that we see here is phenomenal. Usually you get an orange color or a green color or a yellow color, but to get all of these, I'm sure that the photographer is using certain filters to bring out those colors, but nonetheless, what a spectacular show that must be. This is one of the things that's on my bucket list, is to see the northern lights, and all of my journeys in the world, I have yet to see them. All right, so plasma has a lot of uses. You know, it's not just useful for powering the sun. It turns out a plasma is part of fluorescent lights and neon signs. We use neon signs all the time. And basically, when you turn the light on or the lamp on, a high voltage between electrodes of the tube causes electrons to flow. We haven't talked about electrons and voltages and all that stuff. Just know that the light has been turned on and electricity is flowing. We'll talk about what that means in a future set of lectures, not far off, actually. Electricity and electromagnetism is amazingly cool stuff. So this is getting a little ahead of itself, but nonetheless, just kind of take it for granted that this is what happens. These electrons ionize some atoms, forming plasma, right? So you're moving electrons, which means that some atoms are going to lose their electrons to be able to contribute into that flow. Plasma provides a conducting path that keeps the current flowing because it's an ion. The current activates some mercury atoms, causing them to emit ultraviolet radiation. So this is something that is kind of interesting to know, if they activate some mercury atoms. And this radiation causes the phosphor coating of the tube's inner surface to glow with visible light. So it's a kind of a complex reaction that happens, but basically you get this plasma to go, and it emits this ultraviolet radiation, which then in turn activates the coating on it. So it's kind of a multi-step process, as you can see here. Plasma's neat stuff. All right, another thing that we use plasma for is plasma screen TVs. And a lot of people actually have plasma screens on their computers now. So you can get really amazing imagery, very low cost actually, with a plasma screen. So flat plasma TV screens are composed of many thousands of pixels. We haven't talked about color yet. We're going to come to color in, again, a few lectures ahead. But each has 3 separate cells. So each pixel has 3 separate cells. There's a red, a green, and a blue, and each containing a different gas, right? And so pixels are sandwiched between a network of electrodes, and electrodes are charged to produce electric currents flowing through the cells. Now, the electric current, of course, is going to, if it goes through the forms of plasma, the plasma is going to emit some color, and that's what's going to eventually fire off the colors. You know, gases convert to glowing plasmas, releasing ultraviolet light to stimulate the phosphors. And the image on the screen is the blend of pixel colors activated by the TV control signal. And you can get really, really high resolution stuff. This is a lot better than the 1970s and 80s TVs that were around. And it's because with plasma TVs, you're able to get the pixels extremely small, something that you can almost describe as high def, and in some cases beyond high definition. This would be an image of a high definition TV from an advertisement I found online. Pretty spectacular stuff. All right, so that actually concludes our discussion on gases and plasmas. I hope that you found it interesting. There's a lot of stuff that is in gases and plasma that we're not going to be able to get into in a class of this scope, such as the ideal gas law, things like this. But if you have an interest in them, you can learn that stuff in almost any chemistry class. Of course, if you take a more advanced physics class, you'll cover it as well. Okay, with that said, if you have any questions, you can see me on our discussion board, or you can email me directly. Until then, have a good one, and we'll see you at our next lecture. Bye.